Hello everyone, my name is Mohammed Farzanullah and I'm from the University of Ottawa. Today I will be presenting the paper that has been accepted for presentation at GLOBECOM 2024, and the title of our paper is Generative AI Empowered LiDAR Point Cloud Generation with Multimodal Transformer. So this is the outline of our presentation. We are first going to start with the introduction. Next, we are going to discuss some related works. Next, we are going to discuss the methodology. After that, we're going to discuss the simulation settings. Then we will going to see some results. And finally, we will conclude our presentation. So starting off with the introduction. So in the upcoming 6G networks, they are set to incorporate broader frequency ranges, extending from millimeter wave to terahertz frequencies, expanded bandwidth, and more dense array of antennas. These enhancements will allow the convergence of signal detection and telecommunication, each amplifying the effectiveness of the other. So in the future, the communication systems or the base stations, they will be able to utilize many different sensing functionalities such as the visual sensing and localization capabilities, and this is going to enable context aware communications. So basically the sensing uh, based data would be beneficial for many diverse applications such as beam prediction and handover control. And in this case, the data that has been obtained from sensing, it has been shown in some papers that it can be used to perform wireless communication related tasks such as beam prediction and handover control. However, there are some issues with the camera image and the radar. That is, that camera can be less reliable in harsh weather conditions, and the radar produces a sparser representation of the environment. In comparison, LiDAR can provide a more accurate representation of the environment. However, they have not been fully deployed due to their high costs. And in some existing studies, it has been shown to be proven effective for various wireless applications such as beam prediction and handover control. So therefore, there is a need to synthesize or generate LiDAR data with other modalities to enhance the wireless communication performance without introducing extra costs. And in this case, the architecture we use is the multimodal transformer. So the transformer-based generative models are a class of deep learning models that leverage transformer architecture for generating data, and they have been widely used for many NLP tasks. And basically, the transformer architecture relies on the concept of self-attention mechanisms, which allows the model to weigh the importance of different words within a sequence. And a multimodal transformer is an extension of the transformer encoder architecture, which is specifically designed to process multimodal data. And in multimodal transformer, cross-modal attention mechanisms are used, which allows tokens from one modality to attend to tokens from other modalities, helping to learn the intermodal relationships. And so basically, our contributions are that we utilize a multimodal transformer architecture to generate LiDAR point clouds from images and radar data. And in this case, basically, we uh, generate or synthesize LiDAR data from the radar and the camera images. And in this case, we are the first one that uses multimodal transformer to learn the relationship between different modalities. And also, most existing LiDAR generation works, they used an encoder decoder architecture and they can train the complete model. However, we use a pre-trained encoding stage, which reduces the training costs. So moving on to the related works, I will not go into very much detail about these, but like the some works from 10 to 12 have tried to predict LiDAR data from other modalities. However, they do not use the neither do they use the multimodal transformer architecture, or and nor they use pre-trained encoding states. So they are different from our work in that sense. And there are some papers that have used generative AI algorithms for the densification of LiDAR point clouds. However, these papers are for densification of the LiDAR and not the generation. So they are also different from our work. And moving on to the methodology, so in our case, the research problem is that the LiDAR sensor is expensive to install, and it might not be installed, not it might not be feasible to install at every base station. So basically, this calls for a strategy to generate LiDAR data from other modalities, and in this case, we use the radar data and the vision data to generate the LiDAR depth data. And so mathematically, basically, our model will have some parameters w, so mathematically it can be written as that we need to minimize some loss function, and so we need to find the weights that minimize that loss function, which is denoted by w star. And this is our model architecture. So our input is the camera image and the radar data, and the output is the LiDAR image. And in this case, there are three different stages to our model. The first is the encoding stage, and the in the encoding stage, the important thing is that the stage one, or the encoding stage, it completely uses pre-trained models. Then there is the multimodal transformer encoder stage, which is the stage two, which is used to learn the relationship between different modalities. And then the output from the transformer block is passed to stage three, which is the LiDAR decoder, which is used to generate the final LiDAR image. And next, we are going to discuss each of these in a slightly more detail. So for the data pre-processing part for the radar, as it can be seen here, we use fast Fourier transform to produce two different images, which has the range against angle and range against velocity. And the output of these is then passed through the vision transformer to produce the embeddings. And similarly, for the camera images, we use a pre-trained depth model to uh, produce a depth image, and the camera image and the depth image both are passed through vision transformers to produce these embeddings. And these set of four embeddings are then passed through the transformer encoder block, which helps to learn the intermodal relationships between these different modalities. So, moving on, we use the depth anything model, and this allows our model to learn the relative depth of the image, and this provides a greater contextual understanding of the surroundings. And the vision transformer is used to convert the images from all different modalities into an embedding. And in this case, we use the vision transformer that is available on the Hugging Face, and basically it takes any image and converts it into an embedding of size 768. So basically, we have four different embeddings of each of size 768 over here. And then this is then passed to the multimodal transformer encoder block, so which basically is used to learn the intermodal relationships. And in our work, as I mentioned before, the four different embeddings, they are concatenated together and they are passed to the multimodal transformer encoder block. And the multimodal transformer encoder block uses cross-modal attention mechanisms to learn the intermodal relationships. And after that, the output of the transformer block is passed to the LiDAR decoder. And so the LiDAR decoder consists of a series of convolutional layers, and each convolutional layer consists of a transpose convolutional batch normalization and ReLU activation function. And in this case, during each layer, the size of the image is upscaled by a factor of 2. So this produces an output of the required dimension, which is the LiDAR image. And for the pre-processing of the LiDAR image, basically what we do is that we have been provided by 3D point clouds of LiDAR. So we convert that into uh, a 2D heat map, or a 2D map where the two dimensions are the theta and phi, and we try to predict the distance from the origin for all of the possible angles of space. So basically, each of the point of the LiDAR point cloud can be shown by three different parameters, that is theta, phi, and the distance from the origin, which is r. And so basically, our goal is to predict r for each of the possible theta and phi within the space, which covers uh, all of the 360-degree directions in both the theta and phi domain. So we need to predict the distance for all possible angles. And basically, these are interchangeable. So once we have the 2D heat map, or we can generate the 2D heat map, we can then go back and generate the LiDAR point cloud. So this is how we process the LiDAR image. And next, we move on to the simulation settings. So we use the DeepSense 60 dataset for our simulations, and we use the scenario 31 to 34. And in the scenario 31 to 34 consists of an RGB image, radar, 3D LiDAR, and GPS. And in our case, we use the camera, radar, and LiDAR data. And these are the four diverse scenarios. So 31 and 32 data was collected during the day, while the scenario 33 and 34 collected during the night. For the loss function, we realized that the LiDAR image is sparse, and it consists of like most of the more than 90% of the points, they are zero. So it's a very sparse image. And so when we try to train the model using the simple mean squared error, it results in model overfitting, which in which case the model always try to predict zero uh, for all of the possible LiDAR image. And so in this case, we propose a modified mean squared error loss where the denser areas of the LiDAR images are given a higher weight. So in this loss function, the weight to a specific pixel is denoted by alpha I, where I is a pixel. And so it shows that like alpha is like sort of a hyperparameter that we empirically tune. And for the denser parts of the images, we use 10 for the loss function, while at the sparser regions, we use a value of alpha I uh, as equal to 1. And so this basically the concept is to give a higher weight to the denser region so that the algorithm prioritizes to learn the uh, output that uh, in those regions. And so this helps us to uh, achieve better performance. And basically moving on to the hyperparameters. So for each of the four different scenarios, we first split the data into 60% training, 20% validation, and 20% of testing. And basically we train the model for 20 epochs, and these are all of the different hyperparameters that we use. And for the benchmarks, we develop two benchmarks. First is the all zero prediction. So as we mentioned before, uh, most of the image is sparse, more than 90% of the uh, pixels are zero. So first benchmark is that we predict zero for the entire image and see how much error is do we get in that case. And the second benchmark is that we retrain the model but without using the transformer encoder model. So moving on to the results. So this uh, this slide basically first shows the MMSE loss against the epochs during the training stage, and so it can be seen that our loss it decreases as the training progresses, which basically shows that our model is able to learn the relationships and is able to predict the LiDAR image. And secondly, we compare the MMSE for varying the number of filters in the LiDAR point cloud and also with our other two benchmarks. And in this case, we see that the least MMSE is obtained when we use 256, 128, 64, and 64 filters. And when we compare it to the uh, model where we do not use the transformer encoder model, we observe that we obtain 6.47% less MMSE as compared to the model. And this shows that using a transformer model helps to improve the learning. And Next, we also visually compare our predictions to the actual LiDAR images. So we randomly sample a single LiDAR image from each of the four different scenarios and visually compare the actual LiDAR image with the predicted LiDAR image that was predicted by the best model. And so for each of these scenarios, we can see that the model can learn most of the structures captured by the LiDAR image. So in this slide, we show scenario 31 and 32, and in the next, we show scenario 33 and 34. So yeah, so that's all from the results section. So to finally conclude our presentation, so LiDAR sensor is useful for context-aware communications as it can help to optimize many wireless communication tasks such as beam prediction and handover control. And so in this work, we develop a multimodal transformer encoder-based LiDAR point cloud generation model, which allows the generation of LiDAR sensor information from the radar image and the camera image without installing an expensive LiDAR sensor. And so in this case, we use a multimodal transformer encoder model, which facilitates the learning, the relationship between different modalities. And we show that we obtain a lower loss when we use a transformer encoder model, and the visual inspection of the images so that our model was able to learn most of the structures within the LiDAR image for diverse scenarios. So that's all for the presentation. Thank you. And that's all from the presentation. Bye.